Good day, everyone. My name is Dr. Oluwafemi George from the Department of Systems Engineering, University of Lagos. This is a revision class on Engineering Calculus 2. It's on solved examples that are usually encountered in engineering complex analysis, covering topics such as elementary complex analysis, limits, continual differentiability of complex function, Cauchy-Riemann equations, and the complex line integral, and so on. Now, let's look at some solved examples. One, we have to find the limit of z minus exponential pi I over 2 into z over z squared plus 1 as z approaches exponential pi I over 2. 2, we have to find all points of discontinuity of f of z equals tan z. 3, we have to find all the values of z for which exponential z equals to 1. 4, we have to evaluate the integral around the curve C of exponential 2z over z plus 1 raised to power 4 dz if C is a circle with absolute of z equals to 3. And finally, which is number 5, we have to find the residue of cot z over z cubed at z equals 0. Now, let's get started and solve these questions. Number 1 is solution. So if you look at this question carefully, we see that if we put the value of z equals exponential pi I over 2 into the expression, we will encounter a trivial solution. So in order to avoid that, so what we do is to apply the L'Hospital's rule. But before we do that, let's expand this expression. So the first step is to expand the expression. So if we do that, then we have that the limit as z tends to exponential pi I over 2 of z squared over z squared plus 1 minus exponential pi I over 2 z of z squared plus pi plus 1. So now that we've expanded, we can break it down into 2 separate equations, and this gives us apply the limits on each expression. So we have the limits of as z goes to exponential pi I over 2 of z squared over z squared plus 1 minus the limit as z goes to exponential pi I over 2 of exponential pi I over 2z of z squared plus 1. So now we will apply our L'Hospital's rule, and in doing that, we take the differentiation of both the numerator and denominator, and this gives us the limit as z goes to pi I over 2 of 2z over 2z minus the limit as z tends to exponential pi I over 2 of, by the time we differentiate exponential pi I over 2z, we have exponential pi I over 2 divided by 2z. So 2z cancel 2z here. So we have 1 minus the limit of z to exponential pi I over 2 of exponential pi I over 2 divided by 2 times exponential pi I over 2. So exponential pi I over 2 cancel exponential pi I over 2, so that we have 1 minus 1 over 2. This gives us 1 over 2, which is our final answer. So the limit of z minus exponential pi I over 2 into z over z squared plus 1 as z approaches exponential pi I over 2 is equal to 1 over 2. Now, let's look at the second question. We have to find all points of discontinuity of f of z equals tan z. So solution, for f of z equals to tan z, f of z equals to tan z is also equal to sine z over cos z. Typically, we have to show that f of z is undefined. We have to show that f of z is undefined, and to show that f of z is undefined, so we can simply equate cos z to be equal to 0. Then we say that z equals r cos of 0, and from here we know that z is equal to 2k plus 1 into pi over 2. Z equals to 2k plus 1 into pi over 2 for k equals 0, comma, plus or minus 1, plus or minus 2, plus or minus 3, and so on. So for any value of k, we say that the value of cos z will give us 0 for any value of k. So the points we are looking for is z equals 2k plus 1 into pi over 2. Now, the third one, that to find all the values of z for which exponential z equals to 1. Solution. Exponential z equals to 1. So in this case, we need to express the right-hand side of this equation in polar form. So by doing that, we have that 1 is equal to cos theta plus I sine theta. And the next thing is we can compare the real and the imaginary parts on left side with the right hand side. So if we do that, this should be r into, excuse me, it should be r into cos theta plus I sin theta. So by the time we compare the real and imaginary parts on both sides of the equation, we have that r cos theta, which is the real part, equals to 1, and r sin theta, which is the imaginary part, is equal to 0. Then here also we know that r is equal to the magnitude of 1, which is 1 squared plus 0 squared, which gives us 1. So we now say that r cos theta is what? Cos theta, which is equal to 1, and our r sin theta is equal to sin theta, which is equal to 0. Now, we need to find the value of theta that satisfy cos theta equals to 1 as well as sin theta equals to 0. So if we take a look at cos 0 and sin 0, in this case theta equals to 0, we see that this gives us 1 and this also gives us 0. So the value of theta equal to 0 satisfy this equation. So we can write that our 1 is equal to cos 0 plus I sin 0. Likewise, this cos 0 and I sin 0, the 0 can be written also as 1 equals cos 2 pi k. Now this is replacing 0 with 2 pi k plus I sin 2 pi k, where k is an integer. K is an integer from 0. Say k is an integer. So if k is equal to 0, we have cos 0, which retains the original expression. We have cos 0 plus I sin 0, which retains the original expression. If k is 1, we have cos 2 pi plus I sin 2 pi. Cos 2 pi is equal to cos 0. Likewise, sin 2 pi is equal to sin 0. So now, in this case now, we have that 1 is equal to, just divide this page into 2, is equal to cos 2 pi k plus I sin 2 pi k. But if we recall that exponential I theta is equal to cos theta plus I sin theta. So likewise, we can write cos 2 pi k plus I sin 2 pi k as exponential 2 pi k, I 2 pi k. So now we know that 1 is the same thing as exponential I 2 pi k, and this is the same thing as exponential z. Then this gives us that z is equal to I 2 pi k. Note, for k ranging from 0, 1, plus or minus 1, plus or minus 2, and so on. And that is the final expression. Z equals I 2 pi k. Now let's look at the next question, which is that we evaluate the integral around a curve exponential 2z over z plus 1 raised to power 4 dz if C is a circle with absolute of z equals to 3. So let's solve this question. So we have solution. So now, if we let f of z equals exponential 2z and a equals to -1 in the curve tree, integral formula we have that f is power n of a is equal to n factorial over 2 pi I, the integral and the curve of C, f of z over z minus a raised to power n plus 1 is z. So let's call this equation star. Now, when n equals to 3, we have that our f prime prime prime, that is, if we differentiate f of z 3 times of z, it gives us 8 exponential 2z, and our f prime prime at -1 will give us, that is, if we substitute z is equal to -1, we have that this gives us 8 into exponential -2. So now, therefore, equation star becomes 8 exponential 2z, which is equal to 3 factorial. Don't forget, n is 3 over 2 pi I, the integral of exponential 2z over z plus 1 raised to power 4 dz. And the integral that we are trying to evaluate is just this. So if we make this the subject of formula, we have that the integral of exponential 2z over z plus 1 raised to the power 4 dz is equal to 8 pi I exponential minus 2 raised to the power 3. Please, pardon me, this will be exponential minus 2, and this is not there. And that gives us the final expression. Now, let's look at the fifth question and the final question. We have to find the residue of cot z over z cubed as z equals 0. Solution. Residue of f of z, you know that the residue of f of z at a given at a is given by a minus 1, which is equal to the limit as z tends to a of 1 over n minus 1 factorial d is power m minus 1 over dz is power m minus 1 of z minus a is power m f of z. But if you follow this formula, that may be too long. But for the purpose of this question, so we are going to use a Lorentz series. So by Lorentz series, we know that f of z is equal to cos z cot z over z cube. This is same thing as cos z cos z over z cube of sin z and sin of z. And this can be written as, because we have Lorentz expression for cos z and cos z, as well as sin z and sin z. And this is same as 1 minus z squared over 2 factorial plus 0 raised to the power 4 over 4 factorial minus 1 into 1 plus z squared over 2 factorial plus 0 raised to the power 4 over 4 factorial plus 2 divided by z cube into z minus z cube over 3 factorial plus z5 over 5 factorial minus so on is multiplied by z plus z cube over 3 factorial plus z5 over 5 factorial plus and so on. So this can be simplified further to 1 minus z4 over 6 plus over z5 into 1 minus z4 over 90 plus so on. And this is the same thing as 1 over z5 into 1 minus 7z4 over 45 plus and so on. So the residue is equal to the coefficient of 1 over z, and this will give us minus 7 over 45.